some more terminology, solubility. When one substance, solute, dissolves in another solvent, is said to be soluble. We've seen that before, we're just revisiting that. Salt is soluble in water. Bromine is soluble in methylene chloride. When one substance does not dissolve in another, it is said to be insoluble, right? Oil is insoluble in water. The solubility of one substance in another depends on nature's tendency towards mixing, but also the types of intermolecular attractive forces. So those are the two driving forces. There's both an energetic force that can either drive towards mixing or away from mixing, right? In oil and water, it's driving away from mixing. And also nature's tendency towards mixing. There's always a subtle push towards more mixing, but that can be opposed if the energies are too high. So intermolecular forces that we would generally see contributing solubility, dispersion, this is something we've seen before, London dispersion forces like you'd see between alkanes, dipole-dipole interactions, hydrogen bonds, and ion-dipole interactions. These are all interactions that we see in that are favoring solubility. So energy changes in the formation of most solutions, they involve differences in the attractive forces between the particles. There's a tug of war, right? You've got these three different interactions going on. You've got solvent-solvent interactions, solute-solute interactions, and solvent-solute interactions. So you have to consider those three interactions, the self interactions of the solute and the solvent, and the self-other interactions of the solute-solvent. So generally, if the solvent-solute interactions are stronger than the solvent-solvent plus the solute-solute interactions, the solution will always form. The energetics are saying, hey, I like to spread out, you know, I'd rather be interacting with the solvent than I am interacting with this guy over here and the solute, so solution will form. If the solvent-solute interactions are of about equal strength as the solvent-solvent plus solute-solute interactions, then a solution will form. That's an ideal solution. It's like ideal gases mixing. If they don't really care where they are, they don't care whether their neighbors are solutes or solvent, hey, great, just mix. And then finally, if the solvent-solute interactions are less strong than the solvent-solvent plus solute-solute interactions, then it may or may not form. Then you've got a tug of war. You've got the energetic saying, hey, I'm going to stay with other molecules of the solvent. I'm going to stay with the solute, or that may overcome the course of entropy. But if there's just a small dislike of the solvent-solute interactions, a small imbalance such that solute-solute and solvent-solvent are favored over solvent-solute, then entropy might be enough of a push to get things to mix. Okay, so effects of intermolecular forces. For the solvent and solute to mix, you must overcome all of the solute-solute attractive forces. For it to have a uniform mixture, you have to pull apart all of the solute-solute interactions. You have to pull apart some of the solvent-solvent attractive forces, right? Because, you know, if the solute is the minor component, then a lot of the solvent will remain, you know, more or less in contact with another solvent, but it has to break enough interactions to fit solutes in there. These processes are endothermic, right? It's an endothermic process because you've got to put energy in to pull them apart. So at least some of the energy to do this comes from making new solute-solvent interactions. That's an exothermic process. You make new interactions, you go to a lower potential energy, that's exothermic. So the maximum amount of solute that can be dissolved in a given amount of solvent is called the solubility. And there's usually a limit to the solubility of one substance in another, usually because at a certain point of loading in, you start changing the solvent-solvent interaction substantially. And that frequently is where you stop being able to put more in. Gases are always soluble in each other, really, because there's no interactions to overcome. It's all controlled by entropy. Two liquids that are mutually soluble, where it doesn't matter how much you put in, they still mix, are miscible. Ethanol and water are famously miscible solvents. So most alcohols in water are miscible. Oil and water are immiscible because they're not mutually soluble. You can't put as much in. And by oil, we mean essentially any greasy oil. So the solubility of one substance with another varies with temperature and pressure. And we'll talk a little more about this in another segment. So will it dissolve? That's always the question. The chemist rule of thumb is like dissolves like. you will dissolve in a substance that has similar types of intermolecular interactions as you. If you're polar, then you're probably going to dissolve in polar solvents. If you're nonpolar, you're probably going to dissolve in nonpolar solvents. So yeah, chemical dissolve if it has similar structure to the solvent and forms similar types of interactions. Polar molecules on ionic compounds will be more soluble in polar solvents. Nonpolar molecules will be more soluble in nonpolar solvent. Okay. Examples. So just let's look a little bit about this this rule of thumb of like versus like. So let's say methanol. So methanol, CH3OH. It has a little bit of carbon there, but it has a lot of hydrogen bonding. Half of the molecule is hydrogen bonding, and we find that it's completely miscible with water. Here we've got this in the third column. We've got the solubility in water, measured in moles per 100 grams H2O. I don't know why that's the common measure of solubility, but that's what's frequently done. But it turns out to be not very soluble in hexane. Hexane is C6H4, so no H bonds, only nonpolar interactions. Doesn't really dissolve in that because it's mostly hydrogen bonding. If we go to ethanol, which has a little bit more of a greasy tail and can, again, hydrogen bond, it's miscible in both H2O and ethane. Propanol, a little bit greasier, miscible in both water and hexane. And now butanol has more grease to it. It's only sparingly soluble in H2O. You can get a little in, not an enormous amount, but it's miscible in hexane. Pentanol now is not very soluble in water, but is completely soluble in hexane. It's more greasy and less of it is H bonding. Mostly dispersion interactions are about to form. So you can see this sort of how this is compatible with like concepts work.